Okay, the this lecture has to do with control volumes. So you've already become familiar with m dot is equal to rho AV or rho Q, where this is the volumetric flow rate in cubic feet per second or something of that nature. This is the mass flow rate. And in this particular case, it'd be slugs per second. And of course, this is the density that changes. It pretty much changes the cubic feet over into the slugs on this side. You are familiar with this from thermo. And in thermo, you became familiar and you were introduced to this for a conservation. It was conservation of mass. So you were probably told mass in is equal to m dot in is equal to m dot out. Now let's introduce it in a different way. And in this particular way, it's more mathematical. And I'm going to write an equation down without deriving it, and then I'm going to give you some understanding of where it came from. I could go through the derivation, but that may not be as fruitful as trying to obtain a deeper understanding of it. Let's start this way. Okay, so let's say we have a particular quantity B, capital B, is equal to some type of quantity. In our case, the one we're going to do in the short term is the mass. And it's for a system. Now, a system is something along the lines of something where, in thermo you had a piston, and here was your system in here. What we're interested in is something different. Okay, now this is the beta. This is actually the quantity per unit mass. And then we're going to do a closed loop around the entire control system of rho times beta times the velocity. And depends on the way you write this. Some textbooks write it like this, and some textbooks write it like this. But either way you do, these two are intimately tied together. Now, let's start by examining this equation. This is what commonly is called Reynolds transport theorem, and it is basically a transport of some quantity. In our case, it'll be mass, and then well, let's even forget for a moment that we're even dealing with mass. And these are the definitions. This is the beta here, and so the Reynolds transport theorem states that time rate of change of some fixed system over here is equivalent to, let's stare at a particular location in the flow field and let's define a control volume, and these are the quantities through that. Let me give you a typical example. This is probably the easiest example to come up with, and my handwriting is not steady, but that's okay. Let's say you have a particular pipe where you have flow out and flow in. You've decided to come up with what is essentially a control volume, and of course a volume has a surface. So I'm going to let the green designate, or here I'll even do like this. The purple will designate the control volume. So here's the control volume. I've decided. I'm going to come up. Now this is not something that you're going to saw across. This is something, or cut away from the diagram. It's something that's in your imagination. You're going to stare inside of here. Let's even be a little bit more precise and say this is the controlled surface, and the light blue will be the volume. So I would have to color all the inside of here as being the volume. So I'm not going to spend the time to make it perfect, but you get the concept. Now, let's go specifically to our problem. We're looking at mass as being the thing we're interested in. So let's define our quantity B. It'll be M. So beta will be B divided by M, or in our case, it'll just simply be 1. So the Reynolds transport converted into our mass equation will look something like this. dm dt for a system equals to, and I'm going to put another equals to right here because we'll come back to this, time rate of change of rho d volume, integral of the time rate of change of rho v dot n dA. Now these are both vectors, and we're going to deal with those, but in the short term, let's look at this one. This has to deal with our volume. We're going to restrict ourselves to a condition in which the rho is equal to a constant. Okay, if we do, we can pull this density out of this equation, and if it is a constant, we can pull it out in front of the differential, and what we'll be looking at is rho changing d volume. And if we're integrating on the volume, you could even go one step further and say, what's the time rate of change of the volume? Now, if we've decided that our control volume should be fixed in shape and location, then this term by nature just becomes 0. And most of the time that's what you're generally wanting it to be definitely fixed in shape. However, it may be able to move, as you'll later see. So this term equals to 0, and we're just going to write this term back down, and we're going to go back and address what shows up right here. What does show up right here? This is where we make use of the left side here. dm dt for a system that we've decided was going to be fixed mass is going to basically yield you nothing more than 0. If there's no place that mass interjects into this system, then the Eulerian viewpoint, that is, when we track the Lagrangian viewpoint, where we track the particles through and decide that they're going to have fixed mass, this is by definition the case. So this term is basically nothing more than 0. We've already decided that we're going to have a constant density here, and we're left with this. So what does this mean? This is where we're going to take a look at the relationship between two things. We talked about this where these were together. Now I'm down to the point where I'm going to look really specifically at this before I look at anything else. Now, the normal is associated with the area. Now, we've discussed before, and I don't remember which lecture it was in, but that this was the block that we had in which it was in a pressure field, and each of these terms had a normal. And what we had done way back is we summed the forces in the x direction, and that was equal to, call it surface 1. So this was 1, this was 2, and this was 3. We determined that P times the minus, which would be in the opposite normal direction, times the area of 1, which that had a vector component. But in essence, what we ended up with is an area 1 times a minus. I could have moved that to over here, minus n. However, this normal on this end was basically minus j. Usually people put it as a hat. And as a result, you could put the minus here. Take the pressure times the area on this surface, and this normal had a direction associated with it, and this is how this ended up. Now this one has no, so N3 is nothing more than minus j. Now I've made a mistake already. This is I, and I could edit this, but I'm going to leave it in there. So what I'm getting at is that any surface, in our case we look at it this way, let's move it up, n would have some component I plus some component j. This particular one would have nothing more than minus j, given that this was x and y, and this component would be nothing more than minus I. So these, if we were saying that this was the area is perpendicular to the normal, or the normal is perpendicular to the area. So let's take our case in point and take a look at it. First of all, let me spend a minute to try to draw it, and then I'll go in and put my control volume across it. Now I need to put my normals on it. If I were to put normals everywhere, here's what you would see. It would be much like a porcupine, and there are some restrictions here, and I'll spend a moment putting the vectors on there, and then I'll go in and tell you the restrictions. Let me put one right here, and I'll tell you what some of these restrictions are. If you look at a tangent to the surface, it's always perpendicular to the normal vector that sits there. Now, if you have a curved surface, that can become difficult. If you have a straight surface like the inlets and the exit, not a problem. But all along in here, this could be curved in any particular way. So let's take a look at this. I made it a little bit bigger here real quick just so we could take a look at some things. If you're looking at this and you're saying, I want to track the particles through here, what you'll notice is, let's pick one really close to the wall. It will go up, it generally go up and around and through here. This particle end up, try it again. It'll end up going up and out the exit in that particular direction. So these are particle paths, and of course, as you well know, you can take any point in the tangent is the direction of the velocity. Now let's look at this one to be incrementally close to here. So this is very small distance. So for this instant, these particles that are really close to the wall here are in fact tangent to the wall. Now we talked a minute ago that these normal vectors are actually 90 degree to the tangents. So let's take a look at this term, v dot n. Just take any point. Let's zoom in on this point and take a look at it. So here is the wall right there. I've zoomed incrementally close, and here's the velocity vector. And of course, here's the normal. Now, by definition, that we talked about a few seconds ago, these things are 90 degrees to each other. So, if you remember this was the magnitude of the vectors times the cosine of the angle between the vectors. Now, for this case, by definition, the normal is always 1. Now, if this were cosine of 90 degrees, then that just give you 0. And so v dot n here is 0. Now, what does that mean? Well, if I've just tagged a row across it and carried that along, what that meant is if I am looking at this surface being right here, there's no mass flux across that surface. The velocity is only tangential to it, and so there is no mass flux across it. So essentially what this is saying is I want to know the mass flux across the surfaces. And that's why you're integrating over the whole surface. Now this is supposed to be a path integral. So you're supposed to actually start somewhere, say back here, and you run yourself around, you're integrating around the entire surface. Now actually, technically, you have to go in a particular direction, but that being said, that's what you're doing. You're integrating around the entire surface. And if you're good at it, actually, that's a foolish comment. This will end up as exactly the same thing we came up before. Now let me show you that. We start over here, and if you're looking at the surfaces that are associated with the pipe wall, what would you say that the mass flux across those are? Mass flux across the wall is nothing more than 0. So if you were to integrate along where I drew these yellow lines, you would get 0, because everywhere the velocity is tangent and the normal is actually perpendicular to this tangent. The only place that doesn't occur is right here. You have Vn, and right here you have VE for exit, say. Now let's look at the Vn. Go up and take a look at the equation. Now, if you take a look at it, you realize that it's nothing more than velocity inlet, row inlet, velocity inlet, now that's a vector, dotted with the normal, and I'll put I there, area inlet. This is under the assumption that these terms do not vary across this interface right here. If that's the case, they can be pulled out in front, and you end up with this term. Now, we're going to take a close look at this in a second. But let's include the exit as well. Rho of the exit, velocity of the exit, it's still a vector. It has to be dotted with its own normal. And then area of the exit. Let me change this and put this in parentheses as well. Now let's look at this particular term. Okay, it's nothing more than the velocity inlet, magnitude, normal inlet, magnitude, cosine of the angle between them. It just so happens that if you look at that, you have one vector going in one direction and you have another one going in the other, and that's 180 degrees. If you want to look at what 180 degrees or cosine of 180 degrees, that's nothing more than a -1. So what that tells you is rho inlet. Now this is nothing more than equaling to 1. So this is basically velocity inlet magnitude, and then -1, and then area of the inlet. Now, if you look at the exit, velocity of the exit, now you're just looking at this term, normal of the exit. By definition, the magnitude of the normals by definition is 1. Now the cosine here, these two vectors going in exactly the same direction, cosine of 0 equal to 1. So what you get here is velocity of the exit, the magnitude, times area of the exit. Now, not too surprisingly, what you end up with in the final equation is rho inlet the minus sign here plus rho E VE AE, where this is implied that now it's turned into the scalar magnitude. So what you get, rho V area, I've made a mistake there, is equal to rho exit V exit area exit, something you knew before. Now your question might be at this point is, why in the world would anyone introduce something that offers more complexity and yet a little less understanding? This would definitely give you, this whole approach would definitely give you the concept that you may introduce errors in your calculations by taking this approach a little bit differently than what you did before. Here's why this works and why you're introduced to it. Let's take a look at Reynolds transport. Reynolds transport says dB dt for a system is equal to time rate of change of the control volume, rho beta d volume, integral control system where you integrate the entire surface, and rho beta v dot n dA. Now let's make a little chart over here and we'll call it B. Here, I'll try to, here, tell you what, let's move our equation. Alright, so I'm going to make a table. Part of the table is going to be EQN, B, and beta. Alright, let me see if I can, here, let me make this look a little bit better. The betas don't need much room, the B's don't, but the equation does. Okay, so, yeah. So here's the table. And let's take a look at what we already have come up with. For continuity equation, this was, the B was m, the beta was 1. However, we shouldn't call it continuity, we should call conservation of what? This one's going to be conservation of mass. Let's put down mv. This means the beta would be v, and this would be conservation of momentum. Now, there's energy, and there's more and more and more. You can continue these. Most of ours will be confined to these two. There is one other term that we might want to carry, and that is angular or rotational momentum, and that would be r crossed. Let's see, these I should have drawn with a vector, mv, and this would be nothing but r cross v. And there's other ones down here too that you can continue and add as many as you want. Conservation of chemical species, of reactions, of all sorts of things down here. Ours will be confined to these particular three. So this means if I were to specifically look at momentum, what would I see? I would see dmv dt for a system. What is that? That's nothing more than really, if you want to look at what a lot of people say, they could turn this into ma, where it's a vector. Now the more rigorous form is this, but you're used to seeing this. So this is nothing more than sum of the forces. So if that's the case, then you can write down momentum equation just like this. Sum of the forces equal to rho, and now I'm grabbing the right hand side up here and putting down here rho v with the vector. This is the control volume, d volume plus integral over the controlled surface of rho v dot n d area. Now let's take a look at our example, our case back here. Now it's very easy case per se. I'll draw it again. I've been drawing it so many times, but now we're getting the handle of this. So here's our control volume. Here's our normal. I'll just call it N1 and N2. Here is our velocity, V1, V2. Those should have been vectors as well. And let's find out what force would have to be put on this in order to hold it. For example, let's see if I can draw here somebody's hand. Okay, here's his thumb, here's his finger going around it, here's his hand coming off, here's another finger holding this. So I'm trying to draw somebody's hand. So essentially somebody is holding this. This is basically a fire hose. You know, you've had this experience with the garden hose. You turn on the garden hose and you got to hold it, and generally as the water comes out very fast, you're going to have to hold it from it just going wild out in the yard. And if you've had that experience, which most of us have had, then you know what I'm talking about. So basically there's going to be a force on here, and I'm just going to always put this Fx. So here's what I like to do. Just line it up with the coordinate directions. I mean, yes, you could have turned this around, but I'm purposely lining it up with the coordinates. So I'll say Fx is equal to, there's only one force here per se, with an exception. Okay, there is a problem here. Let me back this up, and I'll move my drawing over to the right so we can better see this. Let me erase this. Okay. Let's move it over here. Let's increase its size a little bit because I'm going to start drawing things on it. And for that matter, maybe I better do it a little bit different. Here's what I'm going to do. I'm going to copy it right there. Okay, let me pause this and work. Okay, I finally got it. I've got a duplicate drawing here. Now, the reason I did this, you'll see in a minute. I'll put an equal sign here to mimic that equal sign. Now, this means that my drawing needs to be reworked. Okay, now here's how I'm going to rework it. I'm going to go ahead and take all these off this side. Then I'm going to come over here and say I've got some forces here. So here I'm going to say I got P1A1, P2A2. Now, there are two types of forces that you have on a body. You have generally surface forces and body forces. Now, let's really investigate this situation over here before we go on. Which one of these is surface and which one of these is body forces? Now, at first you may make the mistaken assumption that that is a body force. That is not a body force. Let me tell you why. Let's investigate this, okay? If you've got the steel jacket, let's draw the steel jacket here, or plastic, PVC, whatever. What is happening here is you've got fluid particles coming in here and turning right here and going on out. So all of these except that center streamline are turning. This means that since this thing turned, let's just take this path out there by itself. It did like this. So here's this path redrawn here. In order for it to turn, something had to force it to go in that particular direction. So this means along this surface, which is all we're interested in, we're only interested in this internal part right here. Here's what I mean. This portion right in here. That's all we're interested in. There is a higher pressure. So if you were to draw the pressure diagram here, you would end up with something maybe along this line. You would say, okay, well, I've got a certain pressure here. Here's the pressure. It's going on. And then right around in here it grows because it's forcing the particles to turn. And then it comes down here. Now, what happens down here, according to Bernoulli's equation? Velocity is really high. So the pressure sort of drops here. So you have this high pressure region right here. A little, you start with a certain pressure, you increase, and then you decrease below the pressure that you had here. The point is in these particular zones right here is the only place, if you took that vector out, it was the only one that had an x component. It has an x component and a y component. I'll call it R instead of F. So it has a small x component. You look at the pressure along here, has no x component. Pressure along here, no x component. Not pressure, but the force as a result of the pressure. So my contention is if you look back at this, you will see that this F sub x right here is as a result of the pressure increase along this shoulder of the pipe. If you integrate it along and added it up, that's what you would get, is this value. Now, a body force. Where does the body force come in? It always comes in with the association with the gravity. So here's your body force. Your weight is equal to your volume times, or you have two ways of writing it, but you can just write it that way. A lot of people will write it rho g volume. So let's just write it like that. So again, this force is a result of the pressure on the shoulder of the pipe or reducer or whatever. So with that in mind, that gives you an idea of where each of these forces came from. And now we're going to go on and work on this. And you'll see why I put these apart like this. Let me go down here and draw a delineating line here. And let's just work on the left end. Some of the forces. Well, I've got P1A1 minus P2A2 plus F of x. Now, I could include this, but in the x component, it has no value. Now, the inevitable question might be, and I've had this question before, is why do you have these both showing or drawing into the surface? Why didn't you have one coming in this particular direction, for example? The answer to that is associated with if you had the way I've done this, and if you had working with gauge pressure. If you have an object and say you drew them always in, and you had P1A1 where pressure here was, say, I don't know, 5 psi gauge, and let's say you had P2A2, instead of this it drew a vacuum. You remember the pipe where you were trying to draw the soap up into the container, so this P2 could be minus, say, 5 psi gauge. Well, if you did this in this particular direction, you know, the vector went in this way, then by nature what you're doing by putting a minus 5 times whatever your area is, you're flipping the vector around. So if you write your vectors in this particular way, and that their vectors are always going in like this, then by using gauge pressure, you're always taking care of the situation. In other words, if it becomes a vacuum, like we were talking about right over here, then it flips this vector around. So I always take the easy route, and I always do the vectors in so that any vacuum would be taken care of. So here's my left hand side. What's my right hand side? Now I can put a big long equal sign over here, and now we can make the same argument that this term doesn't appear. Now I've got to take care of a few extra components. Now let's be real specific here. So what I'm going to do is take my row 1. I've called these 1 and 2 now instead of inlet and exit. So velocity 1. And now I need to be very specific, since I've chosen the left-hand side to be the x component. The right-hand side has to be the x component as well, which means that if I took this equation right back here, took off this top, took off that, it would have to be x, and take off this one. So the vector components come from the v's, or if I wanted them to be the y component, I would have that way. Now this is very important. This is a vector equation, so technically in a three-dimensional sense there are actually 3 equations here. More often than not we'll be just dealing with 2 equations, but I have to be very specific here. The V1 x component, V1 dotted with N1 times area 1 plus row 2 V2 x component times V2 N2 and area 2. Now, it just so happens that the rows are the same, so what you end up, and the V1x is nothing more than all V1. This becomes a minus V1 because the dot product, they are both going in opposite directions. A1 plus rho. Since this is going in the positive direction, it's just V2. V2 again, then A2. They're both going together. So the logic is different for each of these, and I'll show you a case in which things are not as straightforward. And so your equation looks just like that. P1A1 minus P2A2 plus, or your eventual goal is to actually find Fx. Fx is equal to P2A2 minus P1A1 plus rho V2 squared A minus rho V1 squared A, and that's it. Now you might want to put in your values if you had one. So conceptually, what you see here is that let's review. We started with this concept that you already knew. We moved on to an introduction of Reynolds transport. Now, I didn't go to prove it. You can go to any sort of textbooks you want to see how they derive it. But what you deal with is you deal with a description of some sort of phenomena that you already had, change in mass with respect to time, change of MV, something like that, and you deal with a control volume and a control surface on the other end. We went through and defined each of our terms and started looking at normal vectors and how you actually implement this in continuity. And when you get all done, you get exactly the same equation you would get back in thermo. At this point, you were probably questioning why you would do something this crazy. Then we moved on into conservation of momentum. And we went down to the point where we can find the force applied to like some fire hose if in fact we had enough of the information like the velocity and the pressures at the ends. Now we're going to go into something a little bit more complicated, but since we've already gone 40 minutes on this video, I'm going to postpone it for the next video.